Hello, I'm Frances Rosamond from the University of Bergen, Norway, and I'm happy to be with you today. I thank the organizers for the invitation. I'm here to talk about parameterized complexity, and I'm happy to see Mike Langston, another invited speaker and an early stalwart, particularly his work on quasi-ordering and applications, which was the origins of parameterized complexity. The first part of the talk discusses parameterized complexity generally, and then I discuss three new emerging areas: solution diversity, the functor project, and decomposing real number hardness results. Here are the frameworks in pictures. The P versus NP framework is one-dimensional, where only the total input size is considered, and most problems in the asymptotic worst case are NP hard. The challenge is met by the two-dimensional parameterized framework, which identifies secondary measurements, the parameter, and tries to confine exponential complexity cost to a function only of these secondary measurements. What we're hoping for is to confine any exponential explosion to a time cost function of a small parameter. Then the running time is expressed as f of k times n to the c, or additively, where k represents the parameter. In the one-dimensional framework, a typical worst-case asymptotic running time would be order of 2 to the n. Suppose n is 100. Well, we can carry out the multiplication, 1,000 times itself 10 times, and with an input size of only 100, the running time is 10 to the 30. That's more than the number of protons in the universe. Suppose the algorithm is improved to 1.47 to the n. Well, that's approximately square root of 2 to the n, which is 2 to the n over 2, and it's still large. What about n equal 200? Well, if you don't have more than 200 people in your database, you're not in business. I'm old enough to have heard Richard Karp speak. When he was a graduate student, he had a job at IBM Labs, and he programmed an exponential time algorithm for the traveling salesman problem. The program was simple, elegant, and clearly correct. He implemented it, hit the run button, and waited. And waited. Nothing happened. This spurred his interest in polynomial time versus exponential, according to his anecdote. In the two-dimensional framework, we might have a parameter of size 10, input maybe 100, still very small. Then f of k n to the c would be 2 to the 10th, 100 squared, which is 10 to the 7th. Well, your PC takes 1,000,000 operations per second, so this takes 1 second, whereas 10 to the 60 will take longer than the lifetime of the universe. The k that we legislate is small. The one-dimensional worst-case framework cannot see k. It can only see n. In the one-dimensional framework, there's no difference between n and k. It sees f of k as f of n. We have to have something different from n in our numerical vocabulary. The parameter can be the size of a query in a database. It can be the number of voters in an election can be large. The parameter can be a small number of candidates. Scheduling problems may include numbers of ships or planes, weather, delivery. The parameter is what is small and seems to be contributing to the exponential growth. In a database, the size of the database is large, but the size of the query is naturally small. Could be the number of species, less than 20, the number of viral variants, the number of jobs to be scheduled, the number of trucks in the fleet, central warehouses, errors in the file. Everybody sitting here can think of 15 more parameters on your own. One way or another in modern life, you can think of 5 more silently as I continue in my talk. Number of old boyfriends or girlfriends, the number of siblings you have in your family, the number of things on your to-do list. The previous examples were of a single value, such as the number of species to fit an evolutionary tree, but the parameter can be a vector of relevant secondary measurements in the problem modeling. Could be a vector of these components of the polyhedron, the parts in a component, linkages, degrees of freedom. Iris Van Rouge is using parameterized complexity in cognitive modeling, cognition. She mentions that the movements of the joints in hand can be approximated by on the order of 20 degrees of freedom in the human body by 43 linked parts. These are small potential parameters. Parameters can be various graph metrics: cut width, tree width, branch width, rank width, clique width. The parameter is 1 over epsilon in a polynomial time approximation scheme. This is a good example because previous examples were about species and warehouses and were concrete, but the parameter can be anything that affects the running time. A natural 20% error means k equals 5. For 1% error, k equals 1 over 1%, which is 100. When Aurora gave his first polynomial time approximation scheme for the Euclidean traveling salesman problem, he found solutions with within a factor of 1 plus epsilon of optimal in time order of n to the 35 over epsilon cubed. For 20% error, think of 35 over 1 over 1/5. And that gives you n to the 4,375. Get the 1 over epsilon out of the exponent. Then the running time is of the form 1 over epsilon n to the constant, FPT. Sometimes a parameterized problem is FPT and sometimes not, in which case we have W1 hardness analogous to NP hardness, modulo A conjecture, extremely similar to P not equal to NP, but happily, very many naturally parameterized problems do turn out to be FPT, and here are some of the positive techniques. And this is a screenshot off Google of some of the books in Springer Proceedings. Notice that there were 234 archived papers in 2020, 1 year. And you may wonder, why was there no data for 2021 presented? The answer is the volunteer collecting the data got overwhelmed and quit. Anybody want a job? Let me know. I am the founder, editor of the Parameterized Complexity newsletter and the website, which also gives you more information about the community. And as I was saying, my archivist quit and I can use you. And we will also be looking for a new newsletter editor soon. So if any of you, if any of you know, ever had to deal with academics, you know what a pain that is. But let me know if you're interested. Let's go on to 3 research directions: solution diversity, functor project, and real number-based hardness results. The theme of the new FPT research direction introduced in solution diversity is that in practical settings of computing, what is needed is a handful of reasonably good solutions rather than a single optimal solution, because practitioners have vital side information to help them choose, sometimes too complicated or even unknown to put into the problem input. As an algorithm designers, we should be talking to practitioners. But if you go talk to a biochemist, I feel sorry for you. The primordial paper was at Ichkai. This is the exploration through the lens of fixed parameter tractability theory, diversity of solutions. And the paper shows a general framework to automatically translate tree decomposition-based dynamic programming algorithms for vertex problems into algorithms for the diverse versions of these problems. For example, a vertex cover identifies vertices to remove that delete all the edges of the graph. If an edge represents a conflict between the two vertices, then deleting the edge removes the conflict. There may be many vertex covers of a graph. An example might be secret agents who must maintain a distance from each other. The captain has a graph of where the agents are with a line between two agents who are too close to each other. And the captain wants a small set of vertex covers that identify agents too close together who must be asked to relocate. The captain has lots of side information, which agents are upstairs on a balcony and difficult to relocate, which agents can move faster than the others. The diverse vertex cover problem we investigated asked to find R vertex covers in a graph G, each of size at most k, such that their diversity is at least D. For example, here we have vertex covers 0, vertex labeled 1, and vertex labeled 4 is a vertex cover. Those three vertices cover all the edges. If we delete those three vertices and the attached edges, we're left with an independent set of vertices. And different diversity measures give different problems, which may or may not be FPT. We used a generalized version of Hamming distance for our distance measure. The vertex covers were represented by a membership or indicator vector. The base set was all the vertices in the graph. So in this case, it would be 0, 1, 2, 3, 4. Then vertex cover A is represented by the membership vector 1, 1, 0, 0, 1. And B is by 0, 1, 1, 1, 0. And they differ in 4 places of the base set, so the Hamming distance between A and B is 4. Our diversity distance was the sum of the Hamming distances between all membership vectors. Work on this very natural parameter of a small number of high-quality solutions has rapidly blossomed. 2 other early papers are by Mateus de Oliveira et al. And Julian Besta et al. The Functor project uses friendly well-quasi-orderings as a general FPT complexity classification technique for parameterized problems. And there is a connection to possibly practical encountered instance complexity via obstruction sets. But if you don't already know well-quasi-ordering, it is a little too technical for this talk. There is a brief write-up in the Festschrift for Hans Bodlander, and there is some commentary in the book by Tim Roughgarden. If you are interested, send an email, and we'll give papers when they become available. Measurements such as heat level, temperature, profit, mix strategies cannot be legislated with arbitrary precision. CPU heat generation is a major issue in computing, where jobs of the same length can generate different amounts of heat depending on their CPU intensiveness. The problem is closely related to scheduling problems, where threshold requirements for different kinds of resources must be observed, such as water or electricity. The methodology is to replace real number modeling with an appropriate ultra-finite arithmetic system, parameterizing on the size of the system. So suppose you bought a mechanical device and the instructions said that this drill cannot be used outdoors when the temperature is 97.359821 degrees centigrade. Or your can of peas says that the use-by date is the 24th of September by 11:30.389046 a.m. It doesn't make any sense. The heat-sensitive scheduling problem models a temperature-aware task scheduling for microprocessor systems, and it asks if all the jobs can be scheduled meeting a specific deadline in such a way that the CPU does not burn up. A model introduced by Kroback assumes that all the heat levels of the jobs are in the temperature interval from 0 to 2. That's that vertical scale there, a real number scale from 0 to 2, and the goal is never to exceed the threshold of 1. Well, the heat levels are real valued, and they're assumed to come arbitrarily close to 2. The updated temperature is a real number. You find it by taking the previous heat level, adding the new heat level, and dividing by 2. And the problem is NP-hard by a reduction with gadgets with real valued heat levels arbitrarily close to 2. But you don't even know how hot the jobs are. The factory does not measure to real number sensitivity. The jobs are hot, medium, cool, cold, or some 10-point scale that we could make. So our method was to quantize it all, the heat level, the updating, the deadlines. This real numbers needs to be made more realistic in the problem modeling. And a similar situation exists for Nash equilibria. You like that picture of John Nash? It looks kind of cute. Do you know the rock, paper, scissors game? Scissors cut paper, paper covers rock, and rock smashes scissors. So the matrix shows that neither player 1 nor player 2 win if they both choose rock, or if they both choose paper, or if they both choose scissors. But suppose you and I are playing and you know I'm going to choose rock all the time. What will you do? Well, you'll choose paper. But when I know that you're going to choose paper, then I change my strategy and decide to choose rock maybe only half the time and scissors half the time. But then you will change your strategy. Well, eventually you decide to choose each 1/3 of the time. I think it over and realize my best strategy is also 1/3, 1/3, 1/3. So now neither of us has motivation to change our strategies. But in real life, you may be betting on the euro beating the yen, but this cannot be calculated with real number precision. To bet on the yen 0.00003% of the time is unrealistic. And there are frictional costs. You have to hire a lawyer and fly partners around to consult. So quantize on the payoff, but also quantize on the commitment and the mix strategy and on the frictional costs. The idea here is to revisit NP hardness results in Nash equilibrium, but also in the theory of voting, election manipulation, and issues in computational social choice, where there are NP-hard problems that posit a collection of voters who strategically order an arbitrary number of candidates. We're working on this with Kitty Meeks at the University of Glasgow. Well, the computing time landscape is evolving as machines get faster and we're deluged with data. How does this potentially affect the two-dimensional theory of PC? This is an interesting and pertinent question, and I guess we will find out. So far, it seems that n is rapidly getting large, but the relevant structural parameters k are relatively conserved. For example, the number k of species does not appear to be going up exponentially, It seems to be going down, which personally scares the heck out of me. On a more mystical note concerning the almost universally relevant structural parameter bounded tree width, Detlef Zeza proved that whenever a family of graphs has a decidable monadic second-order satisfiability problem, the family must have bounded tree width. The proof is based on a theorem of Robertson and Seymour that the families of graphs with unbounded tree width have arbitrarily large grid minors. Well, from a mythical point of view, this seems to say that with arbitrarily large grid minors comes chaos, bedlam, and havoc. I'll leave you with that. We have seen some of the key concepts of parameterized complexity and fixed parameter tractability and some examples of parameters. We have discussed 3 new research directions: solution diversity, the functor project, and deconstructing real number hardness results. And be sure to send me an email if you want to volunteer. Thank you very much.